Okay, problem 3. Whoops, that's not what I want. Let's see. Problem 3 is the one with Tarzan trying to rescue Chug Chug. And so I should tell you, first of all, I've been getting questions about, is this the kind of problem we'll see on the test? Well, yes and no. This is the things we ask you to do in this problem are all reasonable things we could ask you to do on the test. But having this many parts to a problem, it goes A, B, C, D, E, F, I think, is a bit much. So it wouldn't have, it wouldn't have 6 parts. It might have 2 parts, possibly 3 if they're really easy parts. This question came from an exam given for Physics 101 at Rice University, my alma mater, probably somewhere in the neighborhood of 10 years ago. They have all their old tests online. I think a lot of courses probably at a lot of colleges probably do that. So this is an actual, calculus-based physics class problem from a, pretty good university, if I do say so. So why did I say 1? It's not 1. It's problem 3. Anyway, whatever. Okay, so we start, I think, for part A, and I don't have it right in front of me, the problem, so I'm sort of trying to remember what's going on. But for part A, we start with Tarzan up at the top of the cliff, and he's going to swing down to rescue Chug Chug on the vine. What is Tarzan's speed when he gets to the bottom? This is a simple conservation mechanical energy problem. So at the top, we have kinetic energy. Tarzan is 0 because he's just standing there initially, and potential energy comes from gravity, and that is going to be equal to Tarzan's mass times g times capital H, which is the height of the cliff. And then when he gets down to Chug Chug, or when he gets down to Chug Chug's level, his kinetic energy is going to be 1/2 capital M, and I'm going to call his speed just before he hits Chug Chug little u. And that's going to be squared because it's kinetic energy. That's little u as opposed to big U, which I'm using for potential energy. So I'll try to keep those two different. And then, of course, when it gets to the bottom, we're going to call that potential energy equals 0. Remember, you can set potential energy 0 wherever you want. We're picking the river level so that it's makes things easy. And what we can get out of that, since these two, the sum of these two, which is mechanical energy, is conserved, what we can get out of that is that the sum of initial K and initial UG should be equal to the sum of initial K, or final K and final UG. Okay, so, what am I doing? Erase that crap. And so what we'll get there is that, let's see, we're going to get 1/2 big M little u squared equals big M G big H. And that will then get us that, cancel the M's, and the 2 comes over. So little u, which is Tarzan's speed right before he makes contact with Chug Chug, is just going to be the square root of 2G big H. No problem. Okay. So part B, I think, let's see, what does part B ask? I believe part B asks, well, I hope, if I'm remembering this right, it should be asking, yeah, what is the tension in the vine at that point? So this is something that you probably won't need to know for this test coming up, but you will want to know it for the midterm exam. You will want to refresh on that, and that's why we have this on here. The test that was given at Rice, was one test to cover sort of tension and momentum and some circular motion stuff like that. So that's why they have this sort of multi-part problem here. So we do a little free body diagram of Tarzan on the vine. We have the tension force in the vine, which I'm going to call capital F, just because, F for force, why not? And I'll get rid of the little tooth on the F. And then, of course, Tarzan has some weight, so big M times G. And there's no horizontal force acting on him, right? He's sort of swinging through horizontally, so that's fine. So I'm just going to do a y-axis, and sum of forces in the y direction is going to be that tension force minus big M times G, and that's going to equal big M times Tarzan's acceleration. Well, Tarzan's acceleration for circular motion is going to be, remember, Tarzan is swinging down at the bottom of a sort of a circular motion on the vine. The vine is a length of L, so Tarzan acceleration would be the square of his speed at that point, which is u. So u squared over the radius of the circle, which is L. So what we're going to get here, if we take these two things and plug them in together, is that the tension force in the vine is going to be equal to big mg plus big M times u squared over L. And u, remember, we'd already solved for in part A, right? This is u up here. So I wish this little cursor was bigger. I'm trying to use this little cursor to point. It probably looks to you like a gnat. In fact, depending on the resolution you're watching this at, it might not even be visible. That's kind of annoying me. But anyway, so what we're going to get there then is that the tension force in the vine is going to be equal to big M times G plus, and then big M, and then we're going to keep this U squared, so I guess we're going to 2 big M G big H over L. So it's going to be equal to, final version of this, tension force is going to be equal to Tarzan's weight, mg, times 1 plus 2h over L. Okay, so there you go. That's the answer to part B. Part C is then, I'm going to move over. Part C is Tarzan intercepts Chug Chug. Tarzan has a mass of m. So Tarzan has mass of big M. Chug Chug has a mass of little m. Tarzan's initial speed is u. Chug Chug's initial velocity is u. Chug Chug's initial velocity is 0, and they grab each other and cling to each other, so they have the same final velocity, which I'm going to call v. If you are paying attention, you will know this means it's an inelastic collision. Tarzan grabs Chug Chug, they cling tightly to each other, and, you know, Tarzan gets a big smelly ape gripping him. So, initial momentum is going to be m times u, big M for Tarzan times u's initial velocity. Chug Chug has no initial momentum because he's terrified. And then the total final velocity is going to be big M plus little m times v, which means their velocity, or their speed, just after Tarzan grabs Chug Chug is going to be big M over big M times little m times little u. And if I go back, little u was square root of 2g big H. So that means the answer to part C is big M over big M plus little m times square root of 2g big H. Okay, so that's the answer to part C. Okay, part D, I believe, asks what is the tension in the vine at this point. So it's basically the same answer as we had. Well, I can't do that, can I? Okay. So it's basically the same answer we had here, except that instead of plugging in m, we plug in the total m. And let's see. So actually, we should probably go back to let's see. Let me go get it in blue here. Okay. Let's go back to this result, and instead of using Tarzan's mass, we're going to use Tarzan plus Chug Chug's mass, and instead of using little u, we're going to use little v, which we've already found. So we're going to get that the tension force, let me see if I can do this correctly, is going to be mass of Tarzan and Chug Chug, okay, times little g, plus also mass of Tarzan and Chug Chug, times their speed there squared over L. It's the same analysis that got us to the part B answer. It's just a difference, you know, different set of parameters, different mass and different speed. So, boy, this is not looking pretty, but I'm just going to be brave and go through it. So the force is going to be, we're going to have this big M plus little m times G, plus big M plus little m times, and then V squared is going to be, wow, okay, so it's going to be big M over big M plus little m, that's all squared, and then the V squared, stop it, is going to be 2GH, and that all comes over L. Is there any way to make that prettier? I guess we could gather up some G's and maybe the big M plus little m. Still not going to be very pretty. I mean, you could also cancel this big M plus little m with this big M plus little m, but I don't know if that's going to really make it any better. So I'm just going to settle for, the prettier of two ugly things. Big M plus little m plus G, and then 1, so that's where this term goes, this left term, and plus big M little mg. Yeah, so 2h over L times big M over big M plus little m, all squared, close parentheses. Ugly, but there you go. Question E, then, asks, let's see if we can move on. Come on. What? Oh, right. Okay. New page. There we go. Okay, so E asks, what's the minimum value of little h, which is the height on the far side of the cliff, that will allow this plan to work? So, this is just an energy balance in reverse. At the beginning of this sort of last phase of the swing, Tarzan and Chug Chug have kinetic energy of 1/2 total mass times their velocity after they grab each other. And I'm just going to solve this in terms of little v squared, then we can plug in, wow, that's annoying, plug in other things in a moment. And of course they have initial, oh, don't put the stem on. The problem is I got good at putting the stems on my little u's, but now, undo. There we go. I got good at putting the stems on my little u's. The problem is now I'm habitually putting them on my big u's too. So I haven't really made any great strides in, doing this correctly, or in, differentiating them. Okay, so there's, no, that's not our, oh, I cannot do this right. And there is no copy and move around thing here, which is annoying. So initial potential energy is 0, and then at the top of the far side bank, kinetic energy would be 0, and crap, this is getting annoying. Okay, UG is going to be big M plus little m times GH. Okay, so then all we need, of course, is that, to set the sum of these equal, and through an energy balance, what we'll find, oh wait, it's not, oh guys, I am tired, sorry. This is going to be little h. Okay, so, right, through our energy balance, we're going to have, the masses are going to cancel, 1/2 v squared equals little g times h, and then h is going to equal, v squared over 2g. Little h is that. Okay, so there's little h. Now, what was our value for little v? So this is little v, which is, right, so plug in v squared, so we're going to have, stop it, all right, little h equals, now I can't remember what it was. It's going to be big M over big M plus little m squared, and let's just go back and check again, square root of 2gh, so that's going to be 2g big H all over 2g, which means this, it's actually kind of a nice result. Little h equals this dimensionless parameter involving masses, okay? So it's big M over big M plus little m, take the whole thing and square it, and then multiply by big H. So it gets you this sort of semi-sensible result that little h scales with big H, and then also the ratio of the masses matters. Okay, the last question was, what's the maximum tension on the rope? Now this is, that's probably something I shouldn't have asked. To really prove that you found the maximum tension, you'd have to find how the tension varies with position. So you'd have to have, like, say, an angle theta here, okay, and say from the vertical, at any given time, when, say, Tarzan is right here swinging down, you have to find tension as a function of theta. So this is tension force as a function of theta, and then you have to do the whole calculus where you differentiate it, set the derivative equal to 0, find and see if there are any local minima or maxima there. So that's obviously not what we had in mind. Actually, like I said, I just copied this from a test from a college course, so I have no idea what they really wanted. I suppose what you could do is, probably what they had in mind was that one of these two would be the maximum. So this guy here would be one candidate, and this guy here would be the other. And I'm going to leave it as an exercise to the reader to see if you want to try to prove that one of them is definitely bigger than the other. But as for me, I think I will pass. So that's it for the Tarzan Chug Chug problem, and I'll move on to the more interesting or the more bizarre problem.